recording. Okay, so you're all set. Let me just share my screen. I hope you can see my screen, right? So let me just quickly. Fine. Let me just quickly go over what we covered yesterday. Okay, so this is week 12, and I guess this is the last session for this semester, right? Just concluding the entire course today. If you have any doubts, you can ask me at the end. Okay, we can keep around 30 minutes at the end for any Q&As. Now, so in the previous, okay, we have started recording, right? Yes, we have started recording. Now, in the previous class, means tomorrow's class, right? Sorry, yesterday's class, we actually covered this Monte Carlo methods, and we covered TD learning, and they are mostly with respect to policy evaluation. So that means, given a policy, you can compute, and I can just show you the code base also. Let me open up.
Give us small intro and move on. I mean, just couple of 5 minutes or something.
Okay, so this is for week 11. No, week extra. Week extra like this. Yeah. So what we did, we can basically uh, take actions in the environment. For example, sample trajectories, or let's say at the end, right? We can directly interact with the environment by this environment dot step function, right? And our goal was to kind of evaluate the value function, given that I know all the policies, right? Given that I know all possible policies, I can just look through all the policies and ask, okay, whatever is my average value function, I can kind of maintain a list, and based on the maximum value that we got, we can find out what is the optimal policy in that environment. That we did yesterday, right? So basically, what we did, we used this Monte Carlo method for policy evaluation. Okay. So given a policy, I can evaluate how much good or bad it is. And also we have covered the TD learning, or temporal difference learning, uh, and particularly the TD0 variant. Why TD0? So yeah, because see here the VST is equal to VST plus gamma, RT plus gamma. That means it is only one step. Okay. So that's why it's called TD0. This one step thing, that's why it's called TD0. Let's say what is called TD1, if I have another roll up. So instead of just looking into one step in future, I can also write it uh, this up. I can actually also write it like this: RT plus gamma PST plus 1 plus, if I just consider another roll up, gamma square PST plus 2, right? And this is called TD1. So this variant, what we used yesterday, is called TD0. So that means we are only looking up for the immediate future. Okay, so this is the kind of immediate future state. TD1 means then we have to take, so for TD0, we have to take SA, R, S prime, then we can update, right? But for TD1, we have to take SA, R, S prime, A prime, S double prime, right? Then we can take this update. Then we also know the kind of the next to next state transition. Okay. So this is difference between TD0 and TD1. Similarly, you can go ahead with like how many number of TD like kind of lookups you can 1. So the general form is TD lambda. So there will be lambda lookups. Okay. Uh, yeah. So the general form is TD lambda. However, TD0 work like quite well. So in most cases, TD0 is sufficient for this small type of Gridworld environments. Okay. So what we did yesterday mostly was this Monte Carlo methods. That means you keep on interacting with the environment, update your value and number of counts, and can update your total return for a particular state and total number of visits of that state to an average, you get the value, right? Similarly, in TD learning, you are you can update whenever you have this SAR S prime tuple, you can update your value function. So that's how we kind of move from storing the entire history to storing only the trajectory to storing only the kind of immediate transition tuple, right? But all of the algorithms kind of have a shortcoming at the end, right? We discussed that all of them kind of not the control part. We didn't discuss the control part yesterday. So all of these algorithms, and we will discuss these two also. 3D learning, and then this is policy evaluation. Okay. So with this, our uh, our approach was to kind of uh, get the total number of policies and then loop through them, right? And it's not always possible to store all possible policies, right? So for example, you already know the example, right? That 95 state environment would require 2.3 into 10 to the power 49 GB of RAM to store the number of policies possible in memory, right? So it's not possible to store the number of all possible policies all the time, even if you have a very small environment like 96 state environment, right? So another approach similar to what we did for model based, right? So for model based, what we did, we first do policy evaluation. We loop through all the policies, get the policy value v equal to I minus gamma p inverse r. With that equation, you get the v's, and then based on the v's average value, you rank the policies and get whatever is the best policy, right? Then later on, what we did, we start with a kind of 0 0 value, right? And a random policy, then improve our value with the Q function, right? And then based on that, improve our policy. And this loop continues until your previous value and the current value is counted kind of bounded by some epsilon, right? So basically our value function is kind of converged. So value function can be improved like this. So you basically take this point and the previous point, see the difference, how much is the difference. If it is less than epsilon, you stop there. Okay. So that was our approach for model based. In model free also, there is similar concepts. So let's see them. Okay. What is that model free? Maybe I have to download it. Download it. Okay. Download. Okay. So this we did earlier, right? Now here we start from model free control, and those are known as control algorithms. Why? Because you basically control the environment and also keep updating your policy to kind of achieve better and better value. Okay. So basically you control with the current policy, And in the next update, you try to, whatever you experience, right? Based on that experience, you try to improve your policy. Again, control the environment with the updated policy and do this thing over and over until there is no change in the kind of the policy, okay? Or you kind of converge in terms of value function. Okay, so here we cannot decide whether we have converged or not, right? Here we have to kind of uh, play the environment for a certain amount of time, right? Because uh, like there are no Bellman backups or anything here, right? So here we cannot directly check whether my value function has converged or not. Rather, we will kind of depend on the number of uh, episodes we have played. Okay, so if there are large enough number of episodes, based on that, you can kind of expect your policy to be converged. Okay, so as you keep playing more and more in the game, your policy would be like statistically it should become better and better until it kind of converged or saturate. Okay, so let's uh, let's go with Monte Carlo control one. Okay, so we'll follow the same pattern of algorithms like Monte Carlo first visit every visit, then TD has different name in this case. This is called SARSA, and then last Q-Learning. Okay, so what is our goal? Our current goal is to optimize our policy with a high expected reward, right? So that my total return is maximized. Okay, so what are the kind of properties? My actions can have delayed consequences, right? So that's why you are taking that gamma or return as a signal to how much good or bad is a state, right? Rather than the immediate reward. So immediate reward only gives you one step look into future, right? Or not look into future, only one step. If you take this action, what would happen or how much reward you will get. But because our environments can have delayed consequences, right? Then there can be many steps after which we can get the so one step can basically influence the next in next to next future where you will end up. Okay, so basically it can has delayed consequences. So that's why we have to consider the return, not the immediate reward. And return can be controlled by controlling that gamma factor. So if I keep, let's say, gamma equal to 0.9, that statistically my return would represent 10th step return, 10th step reward. So all future 10 steps will be contributing to the return of the particular state, right? If I put gamma to be 0.99, that my then my return is basically considering next 100 steps. Okay. Okay, and then there is a new concept here: exploration versus exploitation. Earlier, because we know the environment, right? We know from each state where we are supposed to go, from the transition dynamics and the reward dynamics. So we don't have to explore much. We already know the environment. We have to just plan. That's why maybe you have seen that what we did to get policy from the Q function, what we did, we basically do argmax, like, right? So let me remind you that part, what we did in that case. Yeah, here. Uh, so in model based methods, right? In those cases, because we know the P and R, we know the probability transition dynamics and the reward dynamics. When we have the Q function, and Q function looks like this, right? You have states in let's say rows, so S0, S1, S2, Sn, and then basically you have action A1, let's small A1, right? Small A1, A2, A3, let's say, or it can be go up to AM, right? And you have, so this entire matrix is filled up with values. So how much return you will expected return you will get if I take action A1 from state 0, right? So basically this is, let's say, QS0 A1, right? This is QS0 A2, something like this. And you have filled all the values. How you get the policy from here? You basically take argmax, right? So why argmax? So I am taking whichever action give me the best value. And what becomes the value? That maximum value is the value, right? So value would be the max. right? Or if you know the policy, why max? So why max is basically representing the value. So we know that value of a state is what? Is basically probabilistic sum of of policy. Let me go with a bigger. Okay, probability sum of pi a given s times QSA. See this equation here. I am taking argmax to get the policy, right? So basically it will give me a probability distribution of like this. Let's say A1, A2, A3. These are three kind of actions possible, right? Then if I take argmax, let's say A2 has the maximum Q value. So my policy becomes like this. So the entire probability mass will be at A2, right? This is one. Both of the other probabilities are zero. So that's why if I'm taking argmax to get the policy, taking max should give me the value function, right? Because other two will be zeros. Only the maximum, let's say probability of A2 will be one. So basically, if I just spread this thing out, right? If I just spread this thing out, it will look like this. Probability of A1 given S, Q S A1 plus probability of A2 given S, Q S A2 plus probability of A3 given S, Q S A3, right? A3. Now, because I have taken argmax, so only one action has the total probability, right? It's not like this. Let's say it's not a fractional, like 0.8% you take A2, other 0.1% you take A1 and A3. It's not like that. It means only this one would be one, right? And other two will be zero. These two, sorry, not this one. This would be also zero. So see, just the maximum one is actually here, right? QSA A2. So that's why taking a max give you value function. If I So basically the logic is this: if I take argmax to get pi, then I can take max to get value function of its value function. Okay. Yeah, this was the logic earlier. But here we cannot do this greedy update. Why? Because see, earlier we know the entire state, right? We have access to all the possible Q values there. All possible Q values we had it. Because we kind of updated the Q values with Q is equal to R plus gamma PV, this equation, right? And V, let's say I started with some random values, but I know the P and R. So whenever I update all the Q values for all the states. But if I am in model free environments, so when I don't have this P access to this P matrix and R matrix, I would be only observing Q values for those states which I visited. So if my maze is like this, let's say my maze is like something like this, let's say, okay. And let's say my goal is here and my agent starts at this position. So if I just, let's say, play in this route, right? Let's just remove all of them. Let's say I explode for a particular trajectory. I explode this path. Okay, I reach the goal. See, I don't actually explore what is it like to if I go with this path. I didn't explore what it is like to go in this path, right? So basically, I don't have Q values for all the states. I only have Q values for those which I have actually visited. So I cannot take a greedy update. I cannot do greedy update. Okay. If I do greedy update, that means I will not explore the environment. There can be more shortcuts to reach the goal. So if you, for example, see, if I just traverse this way, or if I traverse this way, maybe this is the shortest path. Maybe this is the optimal, um, uh, like optimal trajectory it should have, right? But because I choose greedily, it only can find out this part. It will not explore the environment. Okay. It's basically something like when you are in let's say restaurant, you know that they made, let's say, some food item well, right? And you only order that food item so that you will not be able to kind of know which other food items they make well, right?
So in that case,
So
how
that's the kind
similarly,
of dilemma we have at this point.
sir,
So if I want to, let's say for example, let's say you every day you go to a restaurant and then you eat a palak paneer or something, right? You never order uh, something like, let's say, paneer butter masala or something, right? Then you will not know whether the other items are good or bad. Maybe there is something more like better to eat. Okay, because you have not explored it, you cannot say. Now, let's say, so what is our dilemma? So in case of model-free environment, when we don't know anything about all the states, right? We only know whatever we currently explore or experience, right? So there is this concept called exploit, exploit or explore. So exploit mean greedy. So basically you know that this action would be beneficial. From my experience, I know that action A2 will be beneficial. I will take action A2. And explore means I will not take action A2. I will take any other action than A2. I know that A2 is good. That's fine. But I will take some other action. Okay. So basically it's like, uh, I would not say not greedy, not take the best action. Basically, not take the current best action. Okay. So why it is important? See, if I, so what is our kind of how we work? So when, let's say, let's just draw a timeline of our from birth to old, right? So let's say newborn, and see, we don't know how our environment works, right? Or uh, so so basically I don't know how to work until I learn to work, right? So that means I have to go interact with the environment. Every human, let's say, have to interact with the environment to learn more. So basically, we don't have the entire. So you cannot say that if I, so you don't have the total understanding of the world, right? You basically perceive whatever is in front of you, and then based on that to take some action. So that's the perfect example of a model free learning. And this is, let's say, old person. Okay. So let's see how this explore and exploitation is kind of in our brain, how it works. So let's say this is 100%. Okay. This is the axis. Fine. Now explore. So newborns or kind of children explore more, right? They do random stuff. They jump from your bed to your, let's say, your veranda or anywhere. They just do random things, right? So basically they do random actions. So they explore. Okay, if I jump from my bed to the, let's say, the floor, what would happen? Or if I, let's say, uh, what other random things you can think of, right? So basically children do random things, so they explore more. So we can assume that at the beginning people would explore more, and as they age, right, as they age their exploration goes down. We don't explore more now, right? We don't do random things. So basically we so so what I do, I basically wake up, I get ready, come to lab, and then do my research, and then let's say take classes or something like that, and then later on take my lunch, dinner, and then I go to my room, right? This is my kind of a routine. I don't do too much exploration at this point. Not in terms of research. I do a lot of exploration in terms of research, but not in terms of learning the world, right? So see, I basically reduce my exploration as I age. And old people, they don't want to learn any new things, right? They're very old people. So after some age, they will let's say let's keep a hypothetical age like 60 years, right? After 60 years, people try to retire and they don't want to learn new things. Or some people can be exceptional. They may want to learn new things, but in general, I am speaking that they don't want to learn new things. So yeah, this is the exploration graph. Right? This is exploration. Okay. Now, what is exploitation? Exploitation means I know that this would work. I only do that. So basically, you get the reverse thing. Okay. So you basically do one minus exploration, you get the exploitation, right? So basically, you either increase exploration or you either increase exploitation. You cannot increase both, right? They are related like by one minus, like basically 100 minus exploration. So the graph would look exactly same but opposite, right? So something similar to this, right? You get the point that this is kind of exploitation, right? So old people, they exploit more, right? They not in terms of wrong exploitation. They know that okay, if I so let's say uh, they want to go to some place, right? They know that if I take the bus, it will reach me. It will take me there within 3 hours. So they will only take the bus. They will not think about going by train or other options if they have not experienced those things, right? If they have not gone on like kind of boarded train for last 5, 10 to 5 years, they might not prefer that option, right? So basically, they exploit whatever they currently know. They don't kind of go and experiment with stuff. And this is how the learning happens. So basically, the learning happens here in this region. Okay. So let me just round it. So the learning happens when there is lot of exploration. You keep on exploring stuff, adding to your experience, like you add to your experience, and after some point, when you have a good representation of the world, right, or good policy at your hand, you keep on exploiting them, right, and still maybe keep some exploration, right, some small amount of exploration. So there can be instances where old people also take other options, right? They may prefer to go to by train somewhere, right? But not all the time. So basically, there is not always a non-zero exploration, non-zero exploration. But most of the time, they do what they know that it will work, right? So most of the time, let's say 98% of the time, they do whatever they know that it will work, and 2% of the time, they basically do something else, okay, to try new things. Similarly, here we can write that 98% of the time, this children would do random things, and 2% of the time, let's say let's say he's in teaching sessions, right? They cannot do 7 plus 2 equal to 5, right? They will get scolded or something like this. So basically, then they exploit their knowledge. Okay, 7 plus 2 equal to 9. So in some small portion, children also exploit, but that is far less than the exploration part. And in for old people, it is the reverse thing. This kind of notion is very important for us. So why? Because we are also in a same setup, right? We cannot know other parts of the world if I don't explore. And if I only explore, I will not explore means what? I will take random action, right? So if I just only explore, I would not be able to reach to my goal. So in our next algorithms, you will see that this pattern is there. Okay, there is this exploration parameter that you can tune to make your algorithm kind of choose exploration as it plays more and more episodes. So for initial, let's say 10,000 episodes, it can go with a higher exploration and less exploitation. Kind of put together the Q function that has lots of like entries populated, right? It visited lots of different states, and then when it has a good policy, it kind of starts exploiting more and exploiting less. Okay, so that it knows that okay, this path is kind of take me to the goal, so I will only take that part. And like in the last some episodes or something. Okay, so these things are very important, like similar things what we do in our life also. Okay, so let's start with TD learning today first, because uh, what we did and like yesterday was what we first store experience, right? And then based on that, we evaluate a policy that takes a lot of memory, right? Lot of memory. Next, we store trajectory, and that gives me a policy. So basically, this is the offline method, and this is the online method, right? Online Monte Carlo method. That saves memory a bit, right? Saves memory, fine. But if my trajectory is big, let's say my environment has no terminal state, right? My trajectory can go like keep on going like all the way up to infinite number of transitions, right? Then this is also not possible. Saves memory, but may not work, and those are called um, infinite horizon environments. Okay, so the horizon is at infinity, so your episode would never stop. You keep on exploring, just like us, right? Uh, so our episodes also stop obviously when anybody die. They're kind of that's the end of episode for a particular person. But let's say there can be infinite uh, like so for example games like so anything I can think of has kind of a terminal state, but you can think that it can be very far fetched, right? It can uh, so the average lifespan of a human is 80 years, right? 80 or at this point you can think of 75 to 80 years. So that's a lot of transitions if you consider in a second scale to store in memory, right? So basically this method also suffers if my environment terminal state is very far. Then we go for TD learning. So here we only need to store SA or S prime, right? Now see, we don't have to store the trajectory, we don't have to store the experience. Still, we can come up and evaluate a policy. Basically, this is our optimal in terms of storage, optimal storage. We don't have to store anything. It's kind of an totally online method, and it can also work with an like infinite horizon system. Now, the problem was with these cases, we have to look through all the possible policies, look through all pies, right? Now, can I fix this? Because it's not that much helpful. I cannot solve big environments with this. Now let's see what was our update equation and how we can modify it with a Q function. So Q function I can take. So exploitation part comes later. First convert our update equation with a Q function so that we can improve our policy, right? So the update equation for TD0 was what? Vs was updated to Vs plus alpha was the leading rate at T plus gamma Vs prime minus V of S. This was our update equation. Now, how I can just do the same thing with a Q function. So in a Q function, my state would also be associated action. So my QSA would be updated QSA plus learning rate alpha, current reward what I have seen from RT plus gamma. So in the next step, I had S prime and A prime. A prime means the next action I would take minus QSA. See, this also holds, right? This also holds. Now see how what is the tuple I need to update this. S I need S, A I need R, S prime I need, and also let's not write it RT, right? It's R only because I have not written STAT here. And last thing I need is A prime. See this name. This is called SARSA, SARSA, and the algorithm is also named SARSA. Okay. So the next algorithm from TD learning to here, when I can just convert my TD learning thing with a Q function is called SARSA. That's the algorithm name. Okay. So yeah, SARSA. So let's just go and so let's just write the entire algorithm. So what was our previous algorithm? Loop. Let's just go with loop. Loop means it means interact, right? Loop and get these tokens A, S, A, R, S, A, S prime, A prime basically. Get this thing and loop and interact with the environment. Now also update this Q function QSA. QSA plus alpha R plus gamma QSA, sorry, S prime A prime minus QSA. So you do this update. Now how I can improve my policy next? I A given S is actually, and you can think of it's not a probabilistic policy, right? So I can think of pi S. Whatever action I will take, it's basically, so now comes the exploitation part. Okay. So what I will do, um, and see, there is no value function part here, right? So we don't have to think about the value function at all. So we can just think of how I can get my policy, next policy for the state S based on this Q function, new Q, right? Updated Q. That is what I can do. I can take max, or basically argmax. Uh, I can take argmax over all possible actions for QA SA. That's the greedy. Now with this, I will not be able to cover a lot of other states, right? I will just take only one action from a state. So I will not be able to cover the other side-wise states, right? So basically, this is the exploit part. This is the exploit part. Exploit. And next, I can take whatever is the not max action, right? So whatever, the let's say whatever is the not max. So argmax I can take if I just do a set minus A is the total set of actions minus argmax over A USA. right? This is the exploration part. Exploration part. So basically, I will not take that action which has the maximum key value. Now, here comes the trick, that there is a probability called epsilon with which I will take this, and with 1 minus epsilon I will take this. Okay, and I can control this epsilon probability. See, this is the exploration part. Exploration part. This is the exploration part, right? So I can control this probability like this. So this is my epsilon and this is my t. So with time, my probability of sorry, this is 1 minus epsilon. Sorry, this is epsilon. This is epsilon. This is 1 minus epsilon. So basically, initially, the probability of taking other actions than maximum is more, and the probability of taking the optimal action is basically less. Okay, or to simplify this, we can only also consider just not mind set minus other things. Take any action randomly from A. Basically, the exploration part is take random from A. This can also work. Okay, so now the probability mass is distributed like this. So let's say there are four action: A1, A2, A3, A4. Now I know that A2 is the argmax or the base action, right? Now that probability is 1 minus epsilon already. Others would have epsilon divided by mod A, non-zero probability, right? Epsilon divided by mod A, epsilon divided by mod A, and because I'm taking random action, this entire this kind of optimal action would also have that extra epsilon divided by mod A probability. Okay, so basically, with some probability, you also explore other actions, and some probability you also explore the optimal action. And see, when my epsilon starts here, basically this entire, so basically this part would become zero, close to zero. So all the action has say random, the same probability, uniform probability of getting selected. As this thing goes down and down, let's say it's very close to zero, then this becomes close to one, and this all of the other becomes close to zero. So basically it starts exploiting with A2. So here it randomizes the action, randomize actions. Here it selects the action with best Q. Writing is quite so bad. With best Q, QSA. So basically the best action, right? Or greedy action. Here we can say greedy. It's basically random. Okay, so explore. So that's the entire logic. If I just do this, my policy would get updated step by step for every state. Okay? And I have to kind of, as we play along with the environment, I have to kind of have to play a lot of games. Let's say I just play for 10,000 or 1 lakh interactions. And for the first 10,000 interactions, so basically the strategy uh, that kind of is followed in the literature is this, that let's say this is the 10,000th step, okay, and this is the 1 lakh step interaction. So you linearly decay. So in theory, the equation is 1 over t, okay, but it 1 over t is kind of a theoretical bound, that if I go with 1 over t, it kind of um, satisfies a property called GLIE, GLIE, okay, which full form is greedy in the limit of infinite exploration. So, grid in the limit of infinite exploration, yes. So, what does it mean? That at the infinity, it will be completely greedy. So, see, 1 over t would become 0 when t is infinity, right? T is infinity. So, basically, GLIE satisfies that it starts with complete exploration and it ends with complete exploitation. Okay, so this would also work. So let's just start with this, and then I can go you and make, I can kind of show you a optimization that is later on proposed that also satisfies GLIE, but it, it works a bit more kind of efficiently in practice. Okay. So let's start with this approach first, 1 over t. So my epsilon would be this, epsilon would be 1 over t, and t is the in which interaction I'm currently at. Okay. Okay, so you got the algorithm, I guess, right? This is the update equation and this is the policy update equation. And because see there, so for this equation, there is no value function required, so will not compute the value function at all. Okay. Now let's go and see what changed. Now I don't have to loop through all the policies, right? I can only compute the policy from the Q function. I don't have to compute all possible policies, evaluate them one by one, rank them, and take the best one, right? I can kind of start with a random policy, or basically start with no policy at all, build my policy as I'm interacting with the environment. And what changed from the previous interaction patterns is I have to take this next A, this extra A, right, to make this update from here, right? Here I don't have to take the next update. I have to only take SARS prime, right? Then I can do the TD update. But here I have to also take the A prime. That's why it's called SARSA. Okay. Now let's go and implement it. With 12. And let's take some environment which I know is not possible to solve by policy evaluation, right? Let's take this environment. Okay, so how many states are there? State count for 74 states. So what is the possible number of policies in this case? 4 to the power 74. These are the possible number of policies. See, it's not possible to store in memory. Why? Let's compute how many GB it will require. So every policy would have a array of 74 integers, right? So 74 times 32, this many bits, or let's say 4 bytes, right? And then you can divide it with 1024, will give you kilobytes, multiplied with 1024 will give you megabytes, multiplied by 1024 will give you gigabytes, right? Just bracket everything up. So it gives you 3.89 into 10 to the power 37 GB of memory to store the possible number of policies for this in any computer. So my laptop cannot store this. It's like more only 8 GB of RAM. Okay, so this is the number of, write it here. Number of possible policies required this much GB. Okay, so it's certainly not solvable with the previous methods. Now let's see whether this SARSA method works or not. How we can implement it? Let's just go and write an interaction loop first. Okay, so interaction loop while, no, not while, steps. I am talking about steps. So for I in range. Let's say I want to interact for 100 steps, right? So basically 100 time or 1000 time I want to interact, right? Now, first I have to reset the environment. So current state is equal to environment dot reset. My reset my environment to state 0 or any initial state. Now I have to take some action. So let's take a random action for now. So action is equal to environment dot action space dot sample. It gives me a random action. Okay. Now I step the environment. So next state reward comma done. Done means it's ended. Okay. Info is something to keep track of errors. Info would give me. I have to step my action to the environment, which will give me the next state reward done or info. Now see, if I'm done, so if my game has ended, then I have to reset my environment again, right? So here we have to do this. Done is equal to true. Here I would only reset if done is equal to true. See, initially my done is true, so it will reset at the first one, and then only reset again when my done is equal to true, right? So when the environment ends, it resets again. Okay, and here my current state becomes the next state. So my next state becomes my current state basically, right? Okay. Now this is where kind of new episode starts, right? So we have to also kind of store how the episode reward has grown over time. Okay. So let's also store episode reward. And this is where just building how many episodes we see and what is the kind of total reward per episode, just to evaluate our method, how whether it is increasing over episodes or not. Okay. Okay. So see when it is done and it is resetting, my total reward is equal to 0. I can set it 0 here. And when I'm transitioning to the next state, I can just plus my current reward with that total reward. So basically, I keep track of whatever is the kind of this thing, right? Now here, what I can do, I have to not append this total reward equal to 0 here, right? At the initial one, um, I have to only set when one episode ends. Okay, so what I can do, uh, and I is not is equal to 0. See, so first one, the I would be 0. So if these two satisfies, oh no, I have to check it here. See, first I have to set our rewards to 0. Uh, if I is not equal to 0, that means what? It has looped through one episode, right? Then I can save my total reward here and reset total reward. Okay, got it? And also print episode reward episode reward to be total reward, right? And one other things we can also do, that which episode it is currently running on, because we are controlling over number of steps, right? Or number of interaction timestamps, T1, 2, 3 up to let's say 1000. So we can also have to track episode. So this means it's one episode, or let's say more than one episode, right? Um, Current episode is equal to 1. So current episode is equal to 1. Episode, and here I can format current episode. Reward is this, current episode is this, and where I have to increase it, I have to increase it here. When one episode ended, I have, after adding the thing, the current episode is now added once, 1 second, right? Means it's the next episode. Next episode. Another thing that we can write is how many steps was that in that episode, right? So let's say just total reward makes sense. No need to write how many steps were there in a particular episode. Later on, if you need it, we'll write it. But just you get the kind of interaction pattern, right? So every episode you output the total reward it got and then store it later to kind of check whether it increases over time or not. The current everything is fine. Let's run it. Yeah. So we played about 18 episodes. And what was the reward kind of, we can do a plot, import matplot leap dot piplots at tlt dot plot, uh, what was the episode reward. Yeah, so this is my episode reward with a uh, kind of random policy, right? So it doesn't make any sense, it's like totally random. It is fine because I am taking action based on a random policy. This is my random action policy, right? Here we have to update our or use our algorithm to uh, like strategically compute what will be the next good action for this. Now what I have to do, I have to where is it? Yeah, see this algorithm. I have to loop through SAR S prime A prime. This S prime I know, A prime I don't know. I have to take it from the policy. Now let's start with a uh, random policy. Okay, so now we are implementing the SARSA algorithm. Let's write at the top SARSA SARSA algo. Now let's start with a random policy. Pi is equal to uh, so how we can do a random policy sampling. Here we have to just, yeah, here, right, random choice. So this is how we can do a random policy sampling. Just basically for all state, kind of take a random action from the action space. Okay. Now, what will be the here, instead of taking random action, I have to take action from the policy. So pi current state, this is my action from the agent. Instead of random action, this is the action from policy, from basically current policy. Current policy. Now this is fine. I take SA. This is A, right? And A prime I can take it from the policy pi because I have S prime. After here, uh, next, what is the next? I'll state next state. This is okay. What is the next action? Next action, I can take it from pi. Next action, next state, next action. Now see, I have this tuple, entire tuple with me, current state, action, uh, next state, sorry, R, reward, next state, next action, next action, right? Now here I can update that thing. So Q, what is the size of Q? Q size is S comma A, right? So I can create a zero Q at the beginning, okay? Or some, so the initialization of Q is also important. So I can initialize it to zero, right? I can initialize it randomly. Uh, so my, in my opinion, initializing with random values makes more sense because it kind of gives you a random start at the beginning, right? Because anyway, you will take the the pi is computed from Q, right? So if my Q is random initially, then my pi would be most likely random. Okay. Like despite I'm using epsilon greedy or anything like that. So and so this algorithm, where is it? Here, right? This algorithm that okay, 1 minus epsilon will take exploitative decision, and with epsilon probability I will take random actions. This is called epsilon greedy algorithm. Okay. The algorithm name is epsilon greedy. It's, yeah, so this is called epsilon greedy sam policy, epsilon greedy policy over Q. You get pi with an epsilon greedy policy over Q. Okay. Okay. Now here we have this entire thing. Now do the update. Let's do a Q first. Q is a, and let's just write it Q, right? Q is equal to np dot random. Let's initialize it to, let's just initialize it to zero for now. Zero. And the save I have, I don't have np. Np I have, right? Zeros. And the shape I want is s comma a. So number of states is environment dot state count of 74, environment dot action size. The action size gives you 4, I guess. Let's see. It gives you 4 because there are 4 actions possible. So that's how you kind of initialize. Yeah, initialize the Q function. It's state action value function basically. Or you can write it Q is a function. Now here I can do an update like this. Current state. See, I'm currently doing the current state update. I have not converted the current state and the next state for the next loop. Okay. So current state is equal to current state comma xn is equal to Q current state plus the learning rate. So alpha. I have to define the alpha too. Alpha is equal to 0. Let's say 0.0001. Okay. This comes in something like a good standard value. Gamma is equal to 0.99. So we are seeing 100 next steps. And another thing, if epsilon we already know, epsilon would start from 1 and will go to 0, right? 1 over t. And t is the I. So I you can name it as t just to make it more clear, right? Instead of I can just keep it as t, time step. So q plus alpha times reward plus gamma times q qs prime a prime. So next state, and we can just do a something like this. So just to make the computation at the next line. So this slash is the continuation operator in Python. So basically, this entire line will be considered as one after the slash. So reward plus gamma qs next state, next action minus q current state action. So we have the entire update equation. Now based on this, I can update my pi, right? So pi update would be pi current state has to be updated with an epsilon epsilon greedy uh, policy from Q QS between and all the possible actions, right? That we'll see. Now after this Q update, I can sum the current total reward with the total reward and basically move to the next loop. So this thing I have to write. Now epsilon greedy policy, what we can kind of do here. Uh, see, I can just write a function here to be more clear. Def EPSILON epsilon greedy, and it takes a Q function and the current state. Now, what is the best action? Okay, best action is, um, and I have to also give it the action space, right? So action space. The best action I can take by just going argmax over Q. So NP, uh, just do it outside somewhere. Instead of random, just to have populate some values, right? Uh, so this is the kind of arbitrary Q function we have. And if I just want to take from the 0th state, this is the possible Q values. If I do np dot argmax, what is the argument max here? The 0th one, right? It should give me 0. Okay. Now for the first one, it gives me 2. Let's check what was Q1. Yeah, it gives me 2 means 0, 1, 2, this one. Fine. So just doing argmax current state would give me the result, right? So best action would be, what is the argument max for Q current state? Whatever action has the maximum value. And what is the other action? Other action is action space dot sample. And we will say, so the action space, if I just get it from the environment dot action space, it's actually discrete 4 and I can sample from it. See, I can sample from it. If I just do multiple samples, it give me random actions with that sample space. Okay, so I will just use that same feature. So this is the random action. Okay, now here I have to also pass a value called epsilon. EPSILON. And epsilon is 1 over t, that I can pass it from this loop. I have the value for t. So based on epsilon, I would either choose this or I would choose this random action, right? So if I will generate a random value if random np dot random. Okay, if it is less than epsilon, EPSILON, right? So if it is less than, what was our image? Yeah, here with epsilon probability, I will take random action, right? And with 1 minus epsilon, I will take the best action. So if it is less than equal to epsilon, then I will take random action. So from 0 to epsilon value, I would take random. From epsilon to 1 value, I will take the best action. So return random action else. That means what? Here I take from 0 to epsilon, right? SILON epsilon here, and else I will return base taxon, not takes the base taxon. Base taxon. So that means here the mass is from epsilon, right, epsilon to 1. And why? Because this random dot random function generates a uniform random number from 0 to 1. You get the idea, right? How epsilon greedy policy is done. So in case of greedy, the entire mass, the 0 to 1, we take the base taxon, right? But for epsilon greedy, we from epsilon to 1, we take the base taxon, and 0 to epsilon, we take the random action. Okay, and this epsilon value is basically reduced from 1 to 0. So initially, my entire actions will be random. So 0, this would be basically 0 to 1. And as epsilon grows lower and lower, this mass would be reduced to 0, and this mass will be reduced to 1, right? Okay. So this is my epsilon greedy policy. So run, just take the entire definition, remove all these things. Okay. Now current state I have to do is equal to do this update with epsilon value of 1 over t, right? And q, current q value, current state, and action space. Now action space I have to take it out from environment dot action space. PS is equal to, this is what we did. PS is equal to epsilon greedy policy from q, where epsilon is 1 over t. Okay. Now is anything is remaining? Now everything is defined. Let's go to the algorithm once. So we collected this SAR S prime A prime tuple, then we updated Q, and then we get the pi S. So basically we update the policy at state S with an epsilon greedy policy from the Q function, right? Where epsilon is following this GLIE principle. So greedy in the limit of infinite exploration. So okay. So as time would go on, it starts from a high exploding point to basically go on exploding lesser and lesser and exploiting more and more, right? Okay. Now we'll not render or anything. We'll just not go for 1,000. It will go for, let's say, 1 lakh iterations. Okay. So 1 lakh interactions. Okay. So maybe close to around uh, 2,000 or 3,000 episodes. Okay. Now let's run, see whether it works or not. And see, we started with a random policy, right? We started with a random policy and all 0 values for the Q function. And then at the end, after updating pi for every state multiple times for these many iterations, it's supposed to converge to a kind of good policy that takes me from S0 to the goal state, right? Or whatever portion of the environment my agent has covered. Okay. So let's run. Or we can do one thing. We can still print it. Let's see. Let's print it. Division by 0. Okay. So t becomes 0 at the let's start with 1, and from here to here, right? And we have to then update it here. Uh, yeah, now it's fine. So my time starts from 1, not from 0. Okay. Then 1 over t becomes 1. So my entirely you are exploding. Okay. Okay, fine. Everything is fine. Run. Now it is running for 5,000. Oh, it's already done. So it ran for 1095 episodes. Okay. And if I just check the episode reward, this is what how my episode reward look like. So it's not learning anything. I have to maybe learn, like, go for more number of episodes. Okay, or more number of explore, like more number of these uh, steps. So let's go for not 1 lakh, 10 lakh steps. Let's restart and run again. Okay, it's still running. It's going for 10 lakh steps. Okay, it's done. So it ran for how many episodes? It ran for 9,000 episodes, almost 9,500 episodes. Okay, so it played that game for 9,468 episodes, and this is my reward function. So it's basically not improving that much. Okay, so now what I can do to improve this, and let's see what was the emergent policy we have. Environment dot uh, play as human. If I just pass pi, it can give me a representation of the policy. And see, it's not that good, right? It can basically never reach this state unless it is very close to the to the to this, right? It's horrible. Okay. Okay. So what I can do? Let's change the alpha a bit. Let's keep alpha to be 0.001. See whether that would work or not. Okay, done. Let's see. See, it now goes a bit kind of upward, right? So now it's kind of like this. So we can uh, wait. Matplotlib, matplotlib, average graph, average, average line graph. No, not like this. Yeah, I want. If there is any function to do that type of graph, let's check. Yes, yeah, so I want to do something like this type of a visualization. Okay, just to kind of give you an average estimate. So is there? Yeah, let's see. Okay. Uh, okay. Similar plot as ggplot. Given I have a list of values, and I need average from 30 values. not that much helpful. Agree other than what it does, it gives you x and mean. Not helpful. Anyway, so what I can do, I can go with a PD dot. Oh, sorry, I have to input pandas first, pandas as PD, and then PD dot rolling. PD dot not rolling average or something. So basically, what I'm trying to do is do a rolling average on this so that I get a kind of overall trend on this. Okay, so let me just ask rolling average plot on noisy data. Okay, let's try this. I have put this. So n, is it required anywhere? N is not required. Okay. So y becomes our episode reward. APD one. Other things, I guess, and that window I can keep it to, let's say, 30 episodes. Okay. Okay. X is not required. Okay. Yeah. This is what we wanted to build, right? So see, it's kind of going up, but it's very, so it's currently going to zero, right? Zero means we are not getting any negative errors. So that means it can reach to our goal without, or it can reach to our goal at least, right? After uh, kind of roaming around a bit, let's see our policy. What is our policy? Uh, so environment dot play as human file. So this is currently our policy. See, it can kind of take random actions at those places and still see it can kind of reach to our cheese in nearby states, right? So it's still not able to learn how to traverse this region, but it's learned how to traverse this region, right? Now let's change our hyperparameters a bit more. Let's keep alpha same. Let's increase the number of steps, right? Now it, let's say, take uh, 1 crore steps. Okay, and we'll not print because print take a lot of IO, right? Rather, what we can do is use TQDM, so that from TQDM we import QDM, and here I can just do a TQDM, which gives me a kind of progress bar. Okay, progress bar. So now we are going for 10. Now we are going for this many 1 crore kind of interaction steps. Still, the main optimization is still remaining, by which we can basically converge a lot faster. So we don't have to go for 1 crore steps. So currently the problem is this 1 over t, right? Everything is fine, But this 1 over t kind of so if I just draw it, if it like let's keep it running and I draw the function of 1 over t. So 1 over t looks something like this. It looks something like this, or more steep actually. So it looks something like this. Okay. So what is the problem if it looks like this? So basically, you are not exploring enough. So you are, let's say, 1 over 1000, right? 1000 means what? 0.001. So you are exploring only this much time and exploiting for 0.90, sorry, 0.999% of time, right? So basically 0.999 fraction of time you are exploiting and only exploiting for 0. Uh, exploit exploit for 0.999 and explore for 0.001. So this basically my exploration dies a lot quicker than what it is supposed to do. Okay, so that's why you see it's not actually exploring enough. Explores very less amount of time and then only keep on exploiting. So basically, it's unable to learn the environment. It restricts its actions such a way that it's unable to kind of learn what are the nearby states, update their queue function as it kind of explores less. Okay. So what we have to fix here, this one optimization later came on, and that is approximating this GLIE criteria, GLIE criteria. Okay. That is, if I can control how quickly my decay changes. So what changed? Let's say 1 over t dies at 1000. Okay, but I need to go till let's say this is the 10,000 point. Right? I need to go and explore till 10,000 and then kind of keep at a kind of at some non-zero exploration trade-off, right? So basically, what is the optimization here? To start with full exploration, then linearly decay epsilon to a small non-zero value. Now this is the constant, so it will not go to zero. This is a constant. So good values would be, let's say I want to explore 0.01 of the time, all the times, and then I linearly decay from 1 to 0.01, right? Well, basically here I explore 99% of time and 1% of time I explore. Here I start with 100% exploration. I reach to 1% exploration at a linear slope, and I can control the slope based on how much time I want to explore. So let's say I want to explore 10,000 steps, then I want to kind of stick to this ratio of 99% exploration and 1% exploration. Right? So basically, it gives me a control over how many steps I want to explore and then start exploiting. But here, as you see, with 1 over t, it dies really quickly. So basically, it gives us less time to learn. That is what is the problem at this point. So let's see whether 1 crore interactions help learning with 1 over t or not. It's done. Let's see our still running. Yeah. So it learned eventually, right? It learned to reach the see it's kind of more than zero, right? It's not. So the based on this environment, let's see the kind of to reach this goal, right? The optimal policy, if I can consider, it is around I guess 60 to 80. That is the optimal reward. Okay. So what is the current reward, by the way? Episode reward, last reward, let's say it's 71, right? So it learned. Let's see what is the emergent policy. See, it's this policy it learned over 1 crore interaction. So it started with here. So here, then here. Again, go up, right, right, up, right, right, right. So it can reach. So it learned with 1 crore interactions, right? And this is the graph. This is the graph. So for around, so it starts learning till 10 lakh interactions up here, right? And then it kind of keeps on going and going, saturated at. So yeah, that you get the point, right? It takes a lot of time with 1 over t. Now, can I improve this? Yes, copy and paste it to our slides here. Slide. So this is SARSA with 1 over t as epsilon, right? And my learning graph is this. And what is my emergent policy? It's my emergent policy. Oh, sorry, no, wait, clipboard, capture here. Now let's see whether I can do it faster. Now without 1 over with 1 over t, our approaches are like this. Now let's control this epsilon. So epsilon, let's do a function here that basically takes t and give you epsilon. Okay. So there, get epsilon, I EPSI and let's say mean epsilon. Max epsilon is always 1, right? So steady epsilon, STEADY, steady ESILON, epsilon, let's start with 0.01 with 1% at the end. Okay, start with 1, obviously. Steady step, STEADY step. So at which step it should go on steady. Okay, so let's, by default, let's keep it 10,000. So after 10,000 iterations, so steady at 0.01 exploration. So what is the equation? So my equation would look like, let's just go and write this linear equation, right? So what are the initial positions here? It starts with 0x, or t is equal to 1 actually, right? T is equal to 1, epsilon to be 1, fine. And it ends at 10,000 or whatever is the steady state. Let's keep it x steady state, and my y is 0.01, right? So what I want, uh, no, not x steady state, then keep it 10,000. 10,000 is 0.01. So this is my linear line. Beyond that, it is constant 0.01. Okay. So we are not basically continuing this line. We are making it constant here. So till here, if I want to know at any position of x, what is my epsilon value y? So what is the equation? Equation is this epsilon, right? EPS or y. So equation is y minus y1 divided by x minus x1 is equal to y2 minus y1 by x2 minus x1. This is like standard class 12 equation. So y minus y1 is 1, x minus x1 is 1, and then you have y2. Y2 means y2 is 0.01 minus y1 is 1 divided by x2. X2 is this last one, this one. X2 is 10,000 minus x1 is 1, right? So if I just expand this thing out or just put y is epsilon, right? Y is epsilon. So y is equal to 0.01 0.01 minus 1 divided by 10,000 steady state minus 1 times whatever is the intermediate x value, or basically t, right? So x minus 1 and then again a plus 1 from this side to this side plus 1. This is my entire equation. Now if I just replace y with epsilon, so y is actually epsilon and x is basically t, right? And this is current, this is steady state and this is steady epsilon. So basically you write the equation according to this to get the current epsilon value. So, so steady state minus 1 divided by steady state minus t. So steady epsilon minus 1 divided by steady state minus 1 fine um, um, times what? Times x minus t minus 1 t minus 1 plus 1. So just keep this entire thing as bracket and another bracket for the multiplication and then plus 1, right? And this should give you epsilon. Okay, get it? Now if, and also I have to keep this t as input, right? So t comma all those things. If t is greater than equal to steady state, so basically you reach the steady state, then return return your steady state, steady epsilon. Else return this epsilon. Epsilon not epsilon greedy, epsilon. Okay, so this is basically the linear decay, and this is steady epsilon, right? Now I can control up to how many steps I want to explore, and then when I stop exploring, and basically when I majorly stop exploring and start exploring, right? This would kind of make our algorithm more efficient. So instead of 1 over t, I can do a computation of epsilon, ep si lon is equal to get epsilon. I have to pass t steady state epsilon. Let's keep the default values for now. So I am basically exploring till 10,000 steps, and instead of interacting with like for 1 crore, let's interact with 1 lakh. Now it is 1 lakh, right? Let's call this one. 1 lakh, yeah. So I'm basically exploring for 10,000, and then for the 90,000 steps, I'm exploiting. Now let's see whether, and I'm steadily exploring after 10,000 steps with 0.01. Okay. Now let's see how quickly it is done. And so what is the error? Epsilon is not defined. Okay. If P S I. Okay, done. Okay, I have to explore more. See, it's still random, right? So my number of steps should be 10 lakh. And let's say I explore for 1 lakh. Okay. Or let's say I explore for 50,000, not all 1 lakh, 50,000. Okay. And this is my, okay, 38 layers human. Yeah, kind of like this. So it's still not able to learn these initial states, and we can do it by just learning, exploring for a bit more. Okay, so let's explore for, it's going up till 10 lakh. Let's explore for 1 lakh steps. So from 10 lakh, I'm exploring for 10% of the time of the entire gameplay. I am exploring for 10% of the time. Is it improved? No, still I have to go and explore more. So this is 1 lakh and it's 10 lakh. Okay. So what we can improve? What we can improve? Instead of going 10 lakh, let's explore for 2 lakh. Maybe I have to, for the steady explorers, like steady epsilon, I need to make it lower. Is it not 0.01? It should be, let's say, 0.001 or something. Let's see. Yeah, it's going up, right? So 56. Now it's more comparable to the previous performance. Now let's reduce this epsilon here. Let's go with 0.001. Okay. So basically, we are now exploding after like 2 lakh steps. We are exploding at a rate of 0.1%. Run. Okay, 32. Why it is only, okay? It's going this many episodes. Fine. Mm, we have to play more. So let's keep it to 1 crore. Okay. Same number of steps. Okay. So 1 crore number of steps. Uh, so here basically we can control how much should explode. Yellow. Okay. And we'll see whether the curve is kind of going up or what happened. Okay. Maybe alpha value needs to be a bit changed. I have to see. So these parameters actually plays a lot of role. So what could be the good alpha value, right? Or what could be the good steady state value? What could be the good steady epsilon value? These things are kind of hyper parameters, and they can be changed based on like how complex your environment is. So if your environment is very complex, then you can explore more. Okay. And by changing this steady state, you can kind of control that parameter. Let me see. I hope this time it solves the environment only. Oh, I am I'm so stupid. See, here I didn't change the epsilon 1 over t. Okay. So, so it's entirely my fault. Here I should change it to 1 over t. 1 over t to epsilon. Okay. So now again, let's start with 1 lakh. Okay, so 1 lakh and 10,000. That's why I'm a bit confused that why it is not converging quickly. So as per my experience, it converts really quickly. So the 10,000 and the steady state is this fine. So now see, we are again starting with 1 lakh interactions and 10,000 steps exploration. Okay. Oh, now it's really quickly ended. And did I correctly mention everything? Okay. Okay. So let's increase it a bit. Let's go for 50,000 uh, instead of 10,000 and 10 lakh iteration. 10 lakh. Yeah, it looks something like this -7 pairs human. Fine. So 10 lakh, let's increase it to 1 lakh steady state. And we can actually see how this gate epsilon function is actually working. Okay. Let's see whether our implementation is correct. So what we can do, np dot um, ARA arrange 0 to 10,000, 1 lakh, 1 lakh, let's say. This is X, and let's keep Y to be for every value X, every element in X, apply our get epsilon method. Get epsilon method of element, everything else remains same. Let's do plt dot plot Y. Yeah, so this is how it works, right? It linearly decay till what? Till 10,000. Yeah, 10,000 and then continues to with 0.01. Okay, it's working properly. So now we are converting for 10 lakh and 1 lakh as exploration. Okay, not this is the policy it learned. So it learned up till here, not the initial states. So what can be the problem? Maybe I need to will play for more number of episodes. So one good thing I can do, let's see whether reducing the learning rate helps or not. No, reducing learning rate didn't help. So maybe you have to go for 1 crore interactions, and they want to sort of 1 lakh exploration. Okay, now let's go with this. But anyway, our GLIE approach worked. So if I keep my exploration to be 1/t, then sorry, then my algorithm kind of converges and give me a good policy to reach to the cake from the initial state. But see, this kind of don't give us control over how much we can explore, right? So if my environment is more complex, I might need to explore more. Then 1/t would not work. Rather, the current approach what we are doing would work even more, right? So with linear decay, is ILON epsilon, sorry, epsilon, and you have to populate the graphs. Fine. Take 1 more minute. Fine. Linear decay till 1 lakh in 1 crore. And the previous one, it was also 1 crore. Here I are this interaction. 20%. And so there can be many things that impact the entire algorithm. Okay, so where you initialize the Q functions also kind of plays a role. So if I initialize it randomly, the convergence property may change. So it may change more rapidly. Basically, my episode reward may improve very rapidly if I just change the initialization from 0 to random. Okay. So, but these things are kind of experimental. You can check it out. I will share you the code. But it's almost done, 91%. We can see what is the convergent policy. And basically, if I render in between, right? If I render between taking this step actions, but you will see that it is basically playing in that environment. So basically taking action based on the policy, moving the mouse, um, because that takes so much resources, I'm not doing the render. And it converts, fine. It converts. The maximum reward, so last reward it is 67. And if the policy I can check, it's like this. So it's something different, but I can obviously reach to the cake without falling into the traps, right? So go right, down, right, up, up, right, up, right. Yeah, I can reach to the cake from the initial state without falling into these things, right? Yeah. Okay, see, at this state, it is actually avoiding the spike, right? Here also, it is not going that go right. It's going go left, go down, right? So it's basically avoiding those spikes. Okay. Okay. So let's copy this image. put it here. Also the emergent policy. Here. And see, it is actually different from the previous one, right? It's actually different. Okay. So this is what about SARSA. Now there is another algorithm I want to conclude it with, and it's very simple. So one quick change, we have the new algorithm, and that is called Q-Learning. So yeah, so wait here. Yeah, so you got, see this epsilon greedy policy, you kind of get to know this, you get to know this greedy in the limit of infinite exploration theorem, that okay, if I keep my epsilon to be 1 over t, that also would converge if I interact for a kind of significant amount of time, for example 1 crore interactions, right? And at the end, when t when basically I becomes infinity, my epsilon becomes 0. So basically I exploit all the times. Okay? But I start with I is equal to 1. So basically I explore completely at the beginning and then goes to 0 exploration, or basically complete exploitation or greedy, right? So this you know. Now another thing that you know is SARSA, right? This update equals update thing with temporal difference control. Now Q-learning is basically another optimization on the SARSA algorithm. See, in SARSA algorithm, I need to also uh, consider taking the next action, right? The SARSA, SAR, SA means the next action. This one, S prime. So I need this entire tuple, SAR, S prime, A prime. This A prime is extra, and it kind of introduce noise to the system, so that basically my learning algorithm takes longer to learn the optimal Q function, or basically the Q function is required to learn uh, the policy for like optimal policy, right? So it's basically takes longer amount of time to converge because of this kind of A prime sampling. Okay, so what Q learning does, everything is same. Q learning update function changes that will not sample action from the policy, rather we will take the greedy action at the next step. So whatever has the maximum Q value, I will take that Q value instead of taking another action. Got it? So basically you are saying that I will take the best action, not from the policy. I will take the best action. That's the Q learning algorithm. Everything else is same. Okay. Only now you don't need to take A prime. Rather, you basically take the maximum Q value at the next state. Or you can also say take the best action, then do Q S prime best action. Okay. And everything else is exactly same. So this is what Q learning is. So update equation changes as this. QSTAT is equal to QSTAT alpha RT plus gamma max of QST plus 1 minus QST. Earlier it was QST, like QST plus 1, AT plus 1, and AT plus 1 was sampled from the policy, right? So if I just go and check the code, see the next action was basically from the policy, right? By next action. Here is, and that is what is used for the next backup, right? A reward plus gamma times Q next action and next state. Here, instead of doing next state, I want to take the entire Q function for that state and take max. Oh, sorry, let's just not change this thing. Just copy it, paste it below. This, yeah, this is Q learning.
You please repeat what the
Q
difference
learning
between.
algorithm, and then you just change one thing. You don't sample the next action now, and you don't need the next action. You just take the entire Q function for the next state and then just do a max operation on this np dot max. You get the Q function update. So let's with this, let's reduce the number of things to 10 lakh, and here 1 lakh, right? 10 lakh, 1 lakh, that is fine, I guess. So if I just run this, NP is not defined, so I have to, everything is else is same. Okay. Now I'm only going for 10 lakh iterations. And also let's get this here. Hmm. So it is statistically much more faster. Okay. So what is my episode reward -1? It's minus 188 minus 2. Put it random actually. Okay. Let's go for more number of samples. Let's go for 1 lakh. Let's go for 20 or 30 lakh samples, not 50 lakh samples. Okay. Let's go for 1 crore just to compare between all the other ones. Okay, let it run. Okay. So like until it's finished, let's check the other algorithms too, just for a teaser. Okay. There is another algorithm called double Q learning, which is not that much important, and that is the end of model free reinforcement. Okay. So some algorithms that I skipped was these two, and which is very simple. So here, right? See this Monte Carlo evaluation, you can also pair it with improvement. So you can do the same thing, compute return for all the trajectories, get an update, like kind of empirical value of QSA, whatever state you visited, right? You basically update the GSA over NSA for every state. And then based on that, you either do a greedy update or a epsilon greedy update, which can also work. The same thing what you did for Monte Carlo policy evaluation, instead of V, you can compute the Q with the same method and do an epsilon greedy policy update. That would also work, but it's not that much uh, important. So you can go with entire history, then update the Q and update the policy, or you can even go with only getting to know only one trajectory, update the Q and get a new policy, something like this. You can do all variants of Monte Carlo and just add a next step as policy improvement from the queue. Those things will also work. But anyway, this the most important part was this yeah, this SARSA and the Q-Learning. Okay, which is the most optimal model free reinforcement methods. Okay. And this was the, I guess, yeah, this was the trajectory based Monte Carlo estimates. Okay, so basically sample one trajectory, get the returns, do every visitor first visit update for Q functions, and then do a epsilon greedy policy update at the end. Okay. Yeah, so let's whether it's complete. Now 77%. Fine. Is almost done.
पहिला দিনের ব্যবস্থাপনায় পুরসরকারি আয়োজন করা হয়েছে কয়েকদিন ব্যাপী ক্রীড়া অনুষ্ঠান সাংস্কৃতিক অনুষ্ঠান
Okay. Okay, it's done. Let's print the performance. Okay, it converges. Fine. That is the maximum 72 place human. If I see the policy, it's now like this. So Q function, sorry, Q learning also converges with copy image as to a duplicate slide. This Q learning linear epsilon, the epsilon. Screenshot. And this is the emergent policy. Okay, so you can see from these three, these are the kind of their learning curves and their emergent policies, and they are basically they're not same. Okay, they are different in some scenarios. They're different. If you just check for every action at every state, they're bit different. Okay. Okay, so this was all. Yeah. So this is the kind of end of model free reinforcement. So the last algorithm was Q learning. Just update from the SARSA was that we take the kind of maximum Q value at the next step, so that we don't need to sample the next action from policy. Rather, we just need to have this entire like current state, current action, rewarded next step to go. Okay. Okay. And see, we can still, with those algorithms, we can still solve environments which is not possible to, which is like kind of impossible to solve if I go with the previous methods, right? If I go with policy iterations and all. No, it's not policy. So policy evaluation and all. So if I look through all the policies, it's not possible to solve this environment. But with this type of algorithms, I can solve it within under 3 minutes, right? So Q learning takes about how much time? It takes about 4 minutes, right? 3.59 minutes. Basically 3 minutes, 59 seconds. So yeah, so they're very efficient. So basically we don't have to be kind of constrained on the memory now. So we can still solve algorithms which earlier if I want to solve, I need to have 9.83 into 10 to the power 37 GB of RAM. Okay. Okay, so that's kind of the end of reinforcement learning, like model free reinforcement learning. If you have any queries, I'm happy to answer. And I will share the code and everything with you so that you can go and play along with the alpha values, long values, or change stuff, see how it performs. Okay, or change the like kind of the environment itself and see how it adopts, right? Yeah. Any questions? Any questions regarding any topic from okay, so you have not joined the
Can
WhatsApp
you
group.
explain how to use scientific calculator for finding inverse matrix?
For
I have
scientific
left a message there.
scientific calculator, TCS scientific TNTIFS scientific calculator. This is what.
For purpose of finding inverse of a matrix.
No,
Because we need
you cannot compute inverse of a matrix here. You have to kind of get the adjoints and then do a transpose manually. Okay. So see, you will not be given a big matrix. Okay. At worst, you will be given a 4x4 matrix to compute inverse from, right? So
sir,
then
but in
the
assignment there
adjoint.
is 4.
Yeah.
Sir, in assignment 4x4 matrix says.
Yeah, exactly. So in 4x4 matrix, the adjoints will be 3x3, right? determinants.
sir.
Now, like, so just practice by hand. If you can compute the determinant, that would be good. So going for the this calculator is very hectic in those scenarios. Okay, and it's easy. So for a 4x4 matrix in your 12th class, we mostly use a
Yes, sir. Yes, sir. Yes.
mostly not use the calculator to compute that like inverse, right?
Add two row in last and columns.
Exactly,
Not
exactly.
got
And then just do a transpose manually
yes, yes.
after computing all the adjoints. Okay.
So we cannot able to find the inverse and adjoint using this
No,
scientific.
no. This
Okay, sir.
scientific
Thank you.
calculator is only useful for kind of small things or something like this
All
sine
of this.
inverse, cos inverse, all those things, or log
Something. Okay.
computations like this.
Awesome.
Okay. So WhatsApp link group, it should be in the chat. Let me get it. It. So what's the group link? I'm just pasting it there. Yeah. Here I would share the kind of the resources for if so this is the kind of last call, right? So I will share the entire video series and all the resources for this week. Just go over them before. So if you find any uh, like if you find that okay you can revisit any part from the like from the YouTube recordings, you can go and watch the YouTube recordings. Okay. Any other questions? Please explain the difference once again. Could you please explain the difference once again? Oh, difference between Q-Learning and SARSA, right? Oh, so the difference was, yeah, so only this part is the different part that I changed in the code, right? So SARSA update equation was QSA plus alpha at t plus gamma st plus 1 at plus 1. So basically the next action, next state minus the previous Q, right? But Q learning, instead of taking the next action, we takes the maximum Q value for all the actions. So here the action is actually sampled from the policy. Okay. So if the policy has suboptimal action, then this Q function is basically suboptimal. What we do here in terms of Q learning, we takes the maximum Q among all the actions. Okay. So we don't sample from the policy anymore. We take the maximum Q or whatever action has the maximum Q value, that Q value for this loop. Okay. And what we change in the code is only this part. See here, we are basically taking next action from the policy, and here Q next action, next state, right? Next state, next action. But in Q learning, we didn't have that next action anymore. We just basically do np.max of Q next state. So among all the other actions, whatever has the maximum Q value, we place it there. That is the difference from SARSA and Q learning. Everything else is same. Okay. So anything else? Okay. So yeah, you can go and implement other algorithms from here. For example, this Monte Carlo online control, just following this algorithm, right? Just follow this algorithm. So everything is same as earlier, the last day. Only instead of V you have Q, And because of Q, you can do policy updates. So just do the next policy from epsilon greedy, or you can also do this, collect the entire uh, kind of experience, update the Q value, and after we have updated over the entire experience, you go and update the policy. This you can also do. This is basically not an online method, it's an offline method, right? And it's also memory intensive and all. So everything that is done in the previous week can be transferred to a kind of policy update variant, and those are there. So for Monte Carlo, we didn't implemented them because it's very easy to implement them, right? But the new part was this SARSA, this exploration exploitation concept, and the Q-Learning.
So how is this matrix made? How
Yeah.
is it made, this Q matrix?
Can you speak a bit loud? I cannot hear you.
No, how is the Q matrix
Oh,
made?
okay. So initially we we keep Q to be zero, all zeros, and then we updated all values of state and actions with this update equation as we keep on interacting with the environment. Okay, basically we start with all zero values, and then as we keep on interacting with the environment, we basically update the values. Okay, and also keep updating our policy. See, we also started with a random policy. So we started with a random policy and a zero Q function. We keep on interacting with the environment and
That's
then
during
update it.
exploration, no? As part of exploration, it gets updated.
Yeah. So
Okay.
no, in exploitation part also it gets updated, but we don't take those actions which are basically we didn't give us good results earlier, right? We basically take those actions which are based as of now, right? Here. So
No, but that
exploration,
we will know
exploitation.
only during exploration, no? Before exploration, Q will all be zeros, no?
Uh, before no, see, exploration part, exploration part starts from uh, uh, 1 to 1 to 10,000. Okay, and basically you exploration means you keep on trying different actions in a particular state. So basically you keep populating the Q values from zero, it change. So for, let's say if there are four actions, right, it keep on trying all four actions and populate the Q table from the in the exploration part. Okay, and in the exploitation part, it tries to consolidate the Q values. So whatever actions give you good results earlier, it will keep trying on only those actions.
So that means
So
Q is updated during exploitation also.
also, yeah, both of the phases Q get updated, right? Because see this, there is no if condition here, right? It always get executed, whether it is exploding or exploiting. But in exploration phase, the other actions get also updated, right? So let's say if action 4 is not optimal for state 4, right? It also get updated when it is exploding. But in exploitation phase, because it knows that okay, that action didn't give me good results earlier, it will not take that action. So that entry will not be updated in an exploitation phase. But in exploration phase, all the entries get updated. Okay, because it will take random actions, right? Most of the time it will take random action. Yeah, in yeah, most of the time it will take random action. When
Only
express
the
is
action that it is taking, that Q, corresponding Q only will get updated, no?
exactly. So when it is exploding, because it is taking random action, so all the action Q values get updated, and when it is exploiting, only the best action Q value get updated.
So actually, during exploration also, some actions may not be explored, no? So
Yeah,
will the
exactly.
values for that will remain zero throughout?
Yeah, so that's why you are controlling how much you are exploding. So if I go with 1 over t, that would die really quickly, right? So basically, we will not be able to update all possible actions Q values.
No,
So
but
that's why,
how can we ensure optimality in that case? Because if we have left a lot of things, then we cannot tell whether our solution is the best, no?
yeah. So we cannot say any optimality here. So the thing is that in case of model-free reinforcement learning, we cannot guarantee optimality. It is kind of an hyperparameter tuning game. Okay, see, we also tried a lot of hyperparameters, right? So we ended up exploring for 1 lakh steps, but we started with 10,000. So we observed that, okay, if I explore for only 10,000 step, it is not converging. So we go for 50,000 step, we go for 1 lakh steps. And also we also experimented with the total number of interactions, right? So if I go for only 1 lakh interaction, it is not converging. I have to go for 10, like 1 crore interactions to get it converged, right? So these things are kind of hyper parameters that you play with. And same for,
I
so model free reinforcement, it's all about it's more an art than in science. Okay, so the algorithm has kind of an like approximate convergence proof, but it is totally dependent on the hyper parameters you choose.
so actually
So
out of all the machine learning methods, no, which all are really going to give us an optimal solution?
yeah, so optimal solution can be only achieved if you know the environment. If you know the environment, so the model based methods, right? When you know the environment, the P matrix and the R matrix, then you can have an optimality proof that, okay, whatever I am converging to, that is the optimal value function, or that is the optimal Q function. But in case of a model free setting, you cannot kind of guarantee that whatever Q function you converge to is optimal.
So we cannot use this model free method for optimal control problems.
Uh, See, not optimal. You can, so optimal is kind of an a very, uh, so optimal means all the states has a kind of um, your best action, right? All the states reach kind of help you reach to the goal. But in case of model free, if the number of action space, or if the number of state space action space is limited, you can still kind of guarantee that you will reach an optimal policy, right? But you cannot guarantee that you will reach an optimal value function or a key function. Now, optimal control is something else. Optimal control, you can think of that when the action space is continuous, right? Let's say I'm controlling a robot, like kind of telling him to walk properly in a kind of, let's say, noisy terrain, right? In that case, my control becomes the torque or everything in the joints, right? So in that case, my action space can be infinite. So I cannot guarantee even a optimal policy in that case. Okay. So basically it's kind of a gray area at this point. So
Okay,
uh,
sir. Okay.
you can only measure whether a policy is working good or bad by seeing the episode total return. And we observe that, okay, by these algorithms, our episode total return is going to in a kind of increasing and saturating at a particular point, right? And they can be suboptimal. So there are algorithms which solves the method, but it solves the method in a suboptimal way. So it still, so for example, a balancing pole example, right? So it can balance the pole, but it cannot balance it more than 3 minutes. But an optimal policy would balance the pole for infinite time. You get the point, right? So
Yes,
it's
sir. Yes, I got
all
it.
kind of a
Yeah, thanks. Yeah.
approximate thing.
Yeah, yeah.
But these things usually work. So if the world is not that complex, and if it has, let's say, finite state, finite action, then this model free table based methods works mostly fine. And the challenges comes when deep learning take those things take control, right? So when my state space is too big to be stored in a table, or if my action space is too big, right? In those cases, this optimality guarantees are not that much. Those becomes art. So the reinforcement learning later on becomes an art rather than a science. So if somebody has good experience, what is art? But art is when experience count more than knowledge, right? And science is when experience is nothing without knowledge, right? So in reinforcement learning, after a particular point, experience becomes more valuable than knowledge. So how much models we have trained with these algorithms, that's basically give you a good insight of what you should be setting the hyperparameters, or what should be the learning rate, so that my model will converge in this environment. So basically it becomes an art. Whoever has trained, let's say, more models than you in diverse environment, they will be quicker in converging a model in a newer environment. That's the kind of gray area. So it's still like kind of a good area of research. If I can automate the selection of learning rates, if I can automate the selection of the hyperparameters, but you can get the overall point, right?
Yes, so actually one more thing. You were
Yeah,
drawing a graph in which that 1 by t that curve was there, no?
yeah.
What is there? I just wanted to know what is actually the x-axis and y-axis of
So here,
well, x-axis is time only, no? Or
time, and the
the
y-axis is
epochs or
epsilon.
whatever. Uh,
Y-axis is epsilon. The epsilon means how much exploration you do. So 1 over time means you basically, yeah. So this is what we change. So 1 over times mean you start with complete exploration, one by one, right? And then you keep on exploring, and at infinity you become zero explode, right? So epsilon becomes 0. So you exploit totally. And what we changed or optimize on that case, just to control how much we explore, we go with a linear decay till a fixed step, and then constant exploration after that. Okay, so you can also go with 1 over t. That also gives you a good policy. And I guess we also,
actually, you had shown about that old people who were, it was like initially that it'll start with 0 and go
okay,
move towards 1, no?
yeah, here, right?
That one.
So
Ah,
this was an example of how exploration and exploitation change in our life, right? So when we are let's say children, right, we explore more.
no, that I understood. Actually, is this exploitations curve useful anywhere?
Exploitation curve is just 1 minus exploitation. So it's basically the reverse thing,
Okay.
right? And with that's why see in the code also we are only considered about one parameter epsilon, right? The only exploration. And in code also, in code what we do in code, you see here, right? um, you do something like this, that if you are here epsilon greedy, right? If you are within 0 to epsilon, you take random action. If you within 0 to 1 epsilon, then you take best action. So this is basically the exploitation part, and this is the exploration part. So basically one parameter can control exploitation and exploitation trade-off. Okay, so I'm just changing exploitation over time. I'm reducing exploitation over time. That basically increasing exploitation over time. Okay, that's why this curve looks like this. That okay, if I'm going to reduce exploitation, my exploitation automatically increases. XPL yeah. Okay, just so I will share you these notes and everything. If you want to kind of, and everything is written properly here. Okay, so if you want to revisit any concept, for example, this exploitation thing, right? You can go and read these things. We uh, kind of good to get the theoretical background. Anyway, I have explored more, like most of it, like explained most of it. Let's see. And SARSA and Q-Learning we implemented. You can also go and implement the other algorithms, like the algorithm with Monte Carlos and all, based on exploration. Okay. Okay, so I guess it's clear, right? Let me stop recording.
Yes, sir. Yes, very much.
Yeah. Okay.